All right, so today we're going to be diving deep into k-transversals.
Yeah.
With this this paper, Necessary and Sufficient Condition,
Right.
by McGinnis and Sadovek.
Yes.
And they've laid out this condition for the existence of k-transversals,
Yeah.
which is a pretty bold claim. So I guess what's the story here? What's the background?
Well, this paper actually solves a problem that has been lingering in geometric transversal theory for quite a while now.
Okay.
And it's all about figuring out when you can be absolutely sure that a collection of shapes can be sliced through by a single line,
Right.
plane, or a higher dimensional equivalent.
So we're not just talking about any old line, are we? These are like these special k-transversals, I think.
Precisely, yeah.
We've talked about before.
A k-transversal is a k-dimensional affine subspace that intersects every single set in a family of convex sets.
Okay, so just to back up for a second then, a point would be a zero transversal.
Yes.
A line would be a one transversal.
That's right.
A plane, a two transversal, and so on and so on.
Exactly. Into higher dimensions.
All right, so then the challenge then is figuring out under what conditions can we guarantee that such a k-transversal actually exists for a given family of shapes.
Precisely. So for the sort of extreme cases, we have these really classic results like Helly's theorem, which nails down the condition for zero transversals, which is finding a single point of intersection.
A single point. Right.
Yeah. And the Goodman-Pollack-Wenger theorem, which gives us the condition for D1 transversals.
Right. And these are like the cornerstones of this whole area, I guess.
That's right.
Of study. But for years, I mean, finding a general condition for k-transversals, when Ding was like somewhere between 0 and D1, that remained like a mystery.
Right. Big mystery.
Yeah.
And that's the gap that McGinnis and Sadovek finally bridged with their paper.
Wow. Okay. So what's their like secret weapon here? What's the key insight that allowed them to kind of crack this problem?
So the key lies in a new concept that they introduced called dependency consistency.
Dependency consistency.
It's a way of capturing the essential relationships between the shapes and their potential transversals.
Okay.
So
can you unpack that for us a little bit? I mean, what like technically then does dependency consistency even mean?
Yeah. So think of it this way. Imagine each convex set as a point in a higher dimensional space.
Okay.
We're essentially creating a map between these sets and points in a lower dimensional space.
Okay.
And dependency consistency ensures that certain linear relationships between the sets are preserved even after we apply this map.
Okay.
So it's like we're creating a simplified representation of the problem, but in a way that still captures the crucial information about how the shapes are connected.
So I see. So we're not just like randomly assigning points to these shapes. We're doing it in a way that kind of maintains some crucial information about how they're all arranged, right?
Exactly. And it turns out that if we can find such a set of points in a lower dimensional space that satisfies this dependency consistency condition, then we're guaranteed to have a k-transversal in the original space. And vice versa. If a k-transversal exists, we can always find a set of points that reflects this consistency.
So their main theorem is basically saying that this dependency consistency is both a necessary and a sufficient condition for the existence of these k-transversals.
It is.
That's quite a powerful statement.
It really is. It's like having a mathematical blueprint that tells us exactly when a family of shapes can be sliced through in this very specific way.
But I imagine the proof of this theorem is where things start to get really, really interesting.
Yes.
So what kind of mathematical machinery are they using to establish this connection?
Yeah, their proof is a beautiful blend of ideas from topology, geometry, and linear algebra.
Okay, so all the good stuff.
All the good stuff.
All right, so how do they put it all together?
So they use this clever combination of a configuration space, a test map, and two powerful theorems, Borsuk-Ulam and Kerr-Theodori.
Okay, so let's break that down a little bit. What is this configuration space that we're talking about?
Okay, so to understand the configuration space, we need to set the stage.
Oh, okay.
So They use a proof by contradiction.
Okay.
So they start with the assumption that our family of convex sets, we'll call it F, does not have a k-transversal.
Okay, so we're assuming the opposite.
That's right.
What we're trying to prove.
And they also assume that these sets are compact.
Okay.
Which means they're closed and bounded.
Okay, so standard assumptions just to, I guess, make the analysis a little...
Simplify things a bit.
Easier, yeah.
Yeah.
Okay, so we're assuming there's no k-transversal, and we're assuming these sets are compact.
That's right. Now, to make things even more interesting, they embed our original d-dimensional space within a d+1 dimensional space.
Oh, wow. Okay, so they're like bumping everything up a dimension.
Yeah.
Why do they do that?
So it's a clever trick that gives them more flexibility in how they construct this configuration space.
Okay.
So this configuration space is the set of all possible dk dimensional subspaces.
Okay.
Which you can think of as potential directions for our transversal.
Okay.
Within this d+1 dimensional space.
Oh.
Technically, they use the Stiefel manifold,
which represents all possible orthonormal sets of dk vectors.
Okay. The Stiefel manifold, I think I remember encountering that in differential geometry. So that's essentially a way to represent all the possible like orientations of our potential transversal.
Precisely.
Okay.
Now they define a continuous function. We'll call this the test map.
Okay. The test
that takes a point in the Stiefel manifold.
Okay.
So it's a specific set of dk vectors.
Right.
And maps it to a point in a k+1 dk dimensional space.
Yeah.
And this target space represents all the possible ways our family of convex sets can be arranged according to the dependency consistency idea.
So each point in this target space represents a potential arrangement of our shapes.
Yeah.
And this test map kind of connects those arrangements to the potential transversal directions.
Exactly. And here's the crucial part.
They construct this test map so that if it ever hits the origin of the target space, it means we can find a k-transversal after all.
So finding like the zero of this map.
That's right.
Is equivalent to finding the right direction.
That's right.
For our k-transversal.
You got it.
Okay.
And a guarantee that this map actually does hit the origin somewhere, they bring in the Borsuk-Ulam theorem from topology.
Okay. Borsuk-Ulam theorem, no, that's the one about antipodal points on a sphere.
Yes.
Always mapping to the same point.
Right.
In a lower dimensional space.
That's it.
Okay.
So they equip both the Stiefel manifold and their target space with a special kind of symmetry.
Okay.
A Z2 action.
Okay.
Which essentially means that if you flip everything in a certain way, the whole picture stays the same.
Symmetry always plays a powerful role in math. So how does this symmetry guarantee that the test map actually hits the origin?
Yeah, so because of this carefully chosen symmetry, the Borsuk-Ulam theorem guarantees that the test map must hit the origin somewhere.
Wait, so even if we start by assuming that there is no k-transversal,
that's right.
They've shown that we can still find one.
That's right.
That's the contradiction.
Yeah, they've created
a situation where a function that must hit the origin can't hit the origin.
Yeah.
So this contradiction means that their initial assumption that there's no k-transversal has to be false.
Okay, that's really, really clever. But finding the zero of this test map is just the first step, right? I mean, how do they actually connect that back to like a real tangible k-transversal? You mentioned Kara-Theodori's theorem coming in at this point. So how does that work?
Right. So finding the 0 point just tells us that a k-transversal is possible.
Okay.
But we actually need to construct it.
Right.
And Kara-Theodori's theorem helps us with that. Okay. So just to remind everybody, what does Kara-Theodori's theorem even say?
Right. So it says any point in a convex hull can be expressed as a convex combination of a small number of points from the original set. Right.
So like a weighted average.
That's right.
Using points from the set.
Yeah.
So how does that apply here?
Well, so this 0 point corresponds to a point in that k+1 dk dimensional space representing arrangements of our convex sets.
Of our shapes.
Yeah. And Carathédor's theorem lets them express this point as a convex combination of points, each corresponding to a specific convex set in our family F.
So the 0 point, which represents a potential transversal, can be expressed in terms of the original convex sets.
Yes.
That's the connection.
Exactly. And this is where the dependency consistency condition really shines.
Okay.
Because of the way they constructed their test map.
Yeah.
This convex combination tells us exactly how to construct a k-transversal that intersects all of the sets in our family.
So they've managed to weave together this topological theorem about antipodal points with this geometric theorem about convex hulls to prove this very powerful result about k-transversals.
It's really remarkable how these different areas come together to solve this problem.
All right, that's a lot to take in. I think we need a moment to let all that sink in. So let's continue this discussion in the next part where we can delve into the implications of this theorem and explore some of the open problems it raises.
Sounds good. So we've established that this dependency consistency idea is pretty central to understanding when we can find these k-transversals.
Yeah.
But I'm kind of curious about the broader impact of this theorem. Like where does this lead us in terms of other mathematical questions?
That's what I was kind of interested in as well. The paper mentions some fascinating potential applications, especially to problems involving unit balls.
Yeah.
So can you elaborate on that a little bit?
Absolutely.
Okay.
So there's this long-standing problem concerning unit balls and one-transversals that this theorem might help resolve.
Okay.
So imagine you have a collection of unit balls in d-dimensional space.
Okay.
But they're arranged in a specific linear order.
Okay.
Kind of like beads on a string.
Yeah.
But in higher dimensions.
Okay, I can kind of picture that.
Yeah.
So we're trying to find a line, one transversal, that pierces through all these balls.
Yeah.
In the same order that they're kind of arranged.
Exactly. And the challenge is to figure out the minimum number of balls you need to check to guarantee the existence of such a line. Assuming that every subset of that size has a one transversal that respects the ordering.
So if we can find a line that goes through, say, like every group of, I don't know, like 5 balls in the correct order, can we then be sure that a line exists for the entire collection?
That's the idea.
Okay.
And previous research has shown that for pairwise disjoint unit balls, checking every group of Tekken balls is enough.
Right.
So in 3D space, we need to check every set of 6 balls.
Interesting. Okay.
Yeah.
Is that number Tekkens like the smallest possible, or like could we get away with checking fewer balls?
So for disjoint balls, second is indeed the smallest.
Okay.
But there's an open question about whether that number could be smaller.
Okay.
Like 2D1.
Yeah.
If we allow the balls to touch but not overlap.
So a bit more flexibility in their arrangement, but still maintaining that strict ordering.
Yeah.
And this is where McGinnis and Sadovek's theorem kind of comes in.
Potentially, yes.
Yeah.
So remember when K1 in their theorem.
Yeah.
The condition for a one transversal involves checking subsets of size 2D1.
Okay.
Which is very suggestive.
Yeah.
It hints that their techniques, especially the configuration space test map scheme, might be adaptable to tackle this uniball problem.
So it seems like their work is providing new tools that could help unlock solutions to these long-standing questions.
Yeah, absolutely.
Besides the uniball problem, do they point to any other potential applications?
They do.
Okay.
They discuss colorful generalization.
Colorful generalization
of transversal theorems.
Okay.
So imagine instead of one family of sets, you have several, each with a different color. You're then looking for a transversal that intersects a specific number of sets of each color.
So it's like a combinatorial twist on the classic problem.
Yeah, exactly.
Okay, why is this colorful version important?
Yeah, so it has potential applications in areas like resource allocation or network design, where you might have different types of objects or constraints to consider.
Right.
So think of it like a path that needs to hit certain checkpoints.
Right.
But each checkpoint has a color.
Okay.
And you need to hit a specific number of.
Yeah, that makes sense.
Yeah.
Their theorem could be like a stepping stone to a whole theory of colorful transversals.
Exactly. And they believe their dependency consistency framework can be adapted to handle these colorful generalizations, leading to a whole new avenue of research.
Fascinating. So starting with this seemingly like abstract geometric concept, we're uncovering connections to optimization problems. Network theory. I mean, a whole web of mathematical relationships here. But before we wander too far down that path, I wanted to touch on something you mentioned earlier. The fact that their theorem applies to both real and complex spaces.
Right.
What's the significance of that?
Yeah, it's a testament to the power and in generality of their result.
Okay.
Remember how the Goodman-Pollack-Wenger theorem had separate real and complex versions?
Right.
McGinnis and Sadovek provide a unified framework that encompasses both cases.
So their theorem elegantly handles both types of spaces.
Yes.
But for those who might not be as familiar, what do we even mean by complex space in this context?
Right. So in simple terms, a complex space is one where the coordinates are complex numbers.
Okay.
Having both real and imaginary parts.
Right.
And the seemingly small change leads to a much richer geometric structure. For instance, a line in complex space is actually a two-dimensional plane.
A line is a plane
in real space.
Okay, I'm gonna have to ponder that one for a while.
Yeah.
But it highlights how different complex spaces can be.
Right, exactly. Complex spaces have unique symmetries and structures not found in real spaces.
Okay.
And these properties have led to significant results in various fields, not just pure mathematics.
So their theorem is not only solving a long-standing problem in real space.
That's right.
But also giving us like a new tool for exploring these more complex geometric realms.
Precisely.
Wow. Okay.
And it might just be the tip of the iceberg.
Yeah.
This work has the potential to spark a wave of new research.
Here, both theoretical and applied.
This has been a truly insightful discussion.
Yeah.
But I feel like we've only scratched the surface of this dependency consistency idea. Can we dive a bit deeper into like what makes it so important?
Of course.
Okay.
So at its heart, dependency consistency is about preserving essential relationships between the convex sets even when we map them to a lower dimensional space. It's like creating a simplified representation that still captures the crucial features.
Like a blueprint that shows how everything connects.
Exactly.
But in a more like abstract mathematical way.
Exactly.
Okay.
And the key is that the existence of a k-transversal hinges on these underlying dependencies.
Right.
So if we find points in a lower dimensional space that accurately reflect these dependencies, we're guaranteed a k-transversal in the original space. So it's not just any arrangement of points. It has to like encode this relationship network, I guess, of our convex sets.
Exactly. Right. The beauty of their framework is that it provides a precise mathematical language for expressing these relationships. It's a bridge between the geometry of transversals and the algebra of linear dependencies.
Yeah, I'm starting to see the elegance of their approach. It's not just a brute force geometric solution. It's like it's a deeper connection between concepts here.
It is.
But could this dependency consistency idea be applied to other problems beyond k-transversals?
That's a great question, and I think the answer is yes.
Okay.
It has the potential to be applied to a wider range of problems.
Okay.
In geometry and other areas of mathematics.
Like what?
For example, it could lead to new insights in computational geometry.
Okay.
Particularly in shape analysis.
Okay.
And pattern recognition.
So how so?
So imagine you're trying to classify different types of objects based on their geometric properties.
Okay.
This framework could provide a powerful way to capture the essential relationships between different features of those objects, leading to more effective classification algorithms.
So it's a way to see like the geometric essence of things beyond just like simple measurements.
Yeah, exactly.
Okay. Are there other areas where it might be useful?
It could also have implications for graph theory, where the focus is on networks and connections. The dependency consistency framework could provide a new way to analyze and characterize different types of networks, deepening our understanding of their properties and behavior.
It's remarkable how a concept that originated in a specific area of geometry could have such broad applicability.
Yeah.
It speaks to the interconnected nature of mathematics.
Absolutely.
Yeah.
And the authors believe that this dependency consistency framework has the potential to be a transformative tool. It's a great example of how abstract thinking can lead to unexpected and powerful results.
Yeah, this deep dive has certainly been thought-provoking. We've explored a groundbreaking theorem, delved into its proof, and even glimpsed its potential impact on various fields. But I have to ask, what are the limitations of this approach? Are there situations where dependency consistency breaks down or becomes too complex to apply?
That's a crucial question.
Yeah.
While powerful, it's not a silver bullet. One limitation is the complexity of the definition itself. It requires a solid grasp of linear algebra and geometric concepts, which could pose challenges in practical settings, where a more intuitive or computationally efficient approach is needed.
So it's a sophisticated tool that demands a skilled operator, I guess.
Exactly. Another limitation is that the theorem focuses on finite families of convex sets. So this covers a lot of ground, but it doesn't encompass all geometric scenarios. For instance, what happens if we have an infinite number of sets, or if the sets aren't convex? These are open questions that might require extending the framework or developing entirely new approaches.
It seems like their work, while a significant step forward, also illuminates how much more there is to explore in mathematics.
Absolutely. Every new discovery opens up new avenues of inquiry. It's a constant cycle of learning and pushing the boundaries of our understanding.
Well, I'm eager to see where this leads. This deep dive has certainly left me with a renewed appreciation for the power and beauty of mathematical thinking.
I couldn't agree more. And I'm sure our listeners are feeling the same way.
I think one thing that's really come through in this discussion is that even though this theorem provides like a necessary and sufficient condition for the existence of these k-transversals, it doesn't necessarily tell us like how to actually find them.
That's right.
You know, knowing something exists and actually like constructing it are two very, very different challenges altogether.
Yeah, absolutely.
It's like we have a treasure map that says, you know, X marks the spot, but doesn't give us any directions to actually like get there.
Exactly. The theorem tells us whether a k-transversal exists based on this dependency consistency property. But it doesn't hand us a step-by-step algorithm for finding it. So developing efficient algorithms for constructing these k-transversals, particularly in higher dimensions or for complex arrangements of sets. That's a wide open area for further research in computational geometry.
There's fertile ground here for connecting this theoretical breakthrough to like practical algorithms.
That's right.
And that's what makes this area of mathematics so dynamic. I think this interplay between the abstract and the concrete.
I completely agree. This paper by McGinnis and Sadovek is a prime example of that. It's a theoretical leap forward that could pave the way for a whole new class of algorithms and applications.
Stepping back for a moment, I'm struck by how this deep dive into k-transversals has actually revealed like a much broader theme in mathematics.
Yeah.
This idea of understanding relationships between objects and spaces.
That's a profound observation, whether it's connecting algebra and geometry or bridging theoretical results with practical applications.
Yeah.
Mathematics is fundamentally about uncovering hidden structures and patterns.
That's like we're always searching for those unifying principles, those elegant frameworks that help us make sense of the complexity around us.
And that's what fuels the endless fascination of mathematics. You know, there's always more to discover, more connections to forge, more mysteries to unravel.
Well, dear listener, we hope this deep dive has left you with a sense of wonder and a spark of curiosity. Remember, mathematics is not just about formulas and equations. It's about ideas, connections, and the sheer joy of discovery.
Absolutely.
Perhaps you'll be inspired to take these ideas further, to explore the open questions, to forge new connections, and maybe even to find those real-world applications.
That's right.
That link this beautiful theory to the world we experience.
I hope so.
Until next time, keep those minds curious, those mathematical imaginations alive. There's a whole universe of mathematical wonders out there waiting to be explored. Hey there, listeners. You guys been sending in some seriously cool stuff lately.
Yeah, some really fascinating papers to dive into.
This time, you've sent us one that's, well, it's making a splash in the world of geometry. Geometric transversal theory, to be exact.
It's tackling a problem that's had mathematicians stumped for a while,
So the paper's called A Necessary and Sufficient Condition for K-Transversals.
By Daniel McGinnis and Nikola Sadovek.
That's the one. And it's all about figuring out, well, can we be absolutely sure that a specific kind of line, we call it a k-transversal, will cut through a bunch of shapes?
It's not as straightforward as it sounds, though.
I know, right? It seems simple, but it's leading to some pretty deep math.
Definitely.
Okay, let's get into it. So the paper starts off talking about Helly's theorem, a classic in geometry. Can you give us a quick reminder about that one? What's it all about?
Sure. Helly's theorem, it's all about finding this point, this common point, where a bunch of convex shapes overlap. Imagine you've got a bunch of circles, all overlapping, and every time you pick 3 of them, they've got a point in common.
Gotcha. Every set of 3.
Right. So Helly says, if that's true, then all of them, the whole bunch, must have a point in common as well.
Oh, okay. So it's like a guarantee then. If you meet those conditions, you know for sure there's a common point.
Exactly. It's like a geometric safety net.
I like that. A safety net. So how does that tie into the k-transversals?
Well, Helly's theorem, you can think of it as dealing with what we call zero transversals, which are basically points.
Ah, points, like zero-dimensional.
Right. This paper wants to take that idea and go beyond just points to lines, planes, even higher dimensions.
Instead of just points, we're looking for lines, planes that cut through everything.
Exactly. Instead of one common point, we want a line cutting through all those shapes, or a plane, and so on.
So Helly's theorem, that's like the starting point, the foundation.
Precisely. The simplest case. Now, to move past just points, the authors bring up another theorem, the Goodman-Pollack-Wenger theorem.
Okay, things are heating up. What's that one tell us?
So the Goodman-Pollack-Wenger theorem, it focuses on something we call D1 transversals.
D1 transversals.
The D-dimensional space. Yeah. So picture a bunch of shapes on a flat surface, like on a piece of paper, that's 2D. This theorem says you can figure out if a line will slice through all those shapes just by looking at how those shapes can be separated by points on a different line.
Wait, so we're using points to predict what will happen with lines.
It's a really cool idea, right?
Totally. It's like lower dimensions are giving us clues about what's going on in higher ones.
Exactly. It shows you how everything's connected in geometry.
But hold on. Where does a necessary and sufficient condition for k-transversals fit into all this? We've talked zero transversals, a D1 transversals. What about everything in between?
That's what's groundbreaking about this paper. There were conditions for those specific types of transversals, but there was this gap, No one had figured out a condition that worked for all the other possibilities, for all the other K values.
So this paper is filling in the missing piece, huh?
Exactly. And they do it with a new condition. They call it F-dependency consistency.
F-dependency consistency. Okay, that sounds a little intimidating, not going to lie. Can we unpack that a bit?
Sure. So at its core, F-dependency consistency is a way of checking for certain relationships between the shapes, the shapes themselves, and how they can be represented in a lower dimensional space.
So like if I've got a bunch of 3D shapes.
Right. It's like asking, can we arrange points on a 2D plane in a way that reflects those relationships in 3D?
So it's like a lower dimensional blueprint. If that blueprint's good, then we know we can find our transversal.
You got it. It's an elegant way to connect different dimensions and find hidden patterns.
And this works in regular space, the space we live in.
It does. But it also works in complex space, which is, it's a bit more abstract.
Yeah, complex space, we might need a whole other deep dive for that one.
Exactly.
So we've got this magic formula, this F-dependency consistency thing, and it's supposed to help us find those k-transversals. But do they actually prove it works?
Oh, absolutely. The proof, though, it gets pretty sophisticated. They use some powerful tools like the Stiefel manifold and a variation of the famous Borsuk-Ulam theorem.
Whoa, okay, I'm trusting you on the math there. But before we get too deep into that, can we back up a little? Give us a bit more detail about F-dependency consistency. Where is it actually defined?
You're right. Let's look at the formal definition. You can find it in definition 3.1 of the paper. They say, let 0a, d be integers, f(u)(r)c a field, F a finite family of convex sets in FD, and P(u)(k) a finite set of points. We say that F is F-dependency, consistent with D tops in P if there is a map. FP such that for any subset FUEF with F A plus 1, D plus 1, and any Jerkoffine dependencies.
Okay, whoa, that's a mouthful. What are these affine dependencies they're talking about?
So an affine dependency, it's a way to describe a relationship between points. Like if you have 3 points all on a line, that's an affine dependency.
Okay, so like a pattern or a rule that those points follow.
Right. And this definition, it's saying that if certain affine dependencies hold for the points in a lower dimensional space, then corresponding dependencies must also hold for the actual shapes in the higher dimensional space.
So it's like those points in the lower dimension are a guide. They're encoding the relationships between the shapes in a higher dimension.
That's a great way to think about it. And if that encoding is, consistent in this specific way, then we're guaranteed to find our k-transversal.
Gotcha, like a mathematical guarantee.
Precisely.
Now, you mentioned the Stiefel manifold before. I got to be honest, not really familiar with that one. Can you shed some light on what it is?
Of course. So the Stiefel manifold, it's a space that represents all the possible ways you can orient a set of perpendicular vectors in a given dimension. Picture 3 arrows all at right angles to each other.
Like the X, Y, and Z axes.
Exactly. The Stiefel manifold would be like all the possible ways you could rotate and position those arrows in 3D space while keeping them perpendicular.
So it's a whole catalog of possible orientations.
You got it. And in this paper, they're looking at specific sets of these vectors. They call them DK orthonormal frames.
DK orthonormal frames.
It just means sets of DK mutually perpendicular vectors in D+1 dimensional space.
Okay, I'm following along. They use the Stiefel manifold, they use these frames, and that's important for their proof.
It's a key part. They create a special mapping using this, which is essential for their proof.
All right, and what about this Borsuk-Ulam theorem you mentioned? Where does that fit in?
The Borsuk-Ulam theorem, that's a really powerful tool in topology.
Topology, that's the study of shapes and spaces, right?
Yeah. Right. It basically says that if you take a sphere, like a basketball, and try to flatten it onto a flat surface, there will always be at least 2 points on opposite sides of the sphere that end up on top of each other.
So no matter how you squash that sphere, 2 points got to touch.
Exactly. They use a version of this theorem that applies to the Stiefel manifold instead of a sphere.
Oh, interesting. So they're not dealing with actual spheres here.
Not in this case, no. And this allows them to show that under the right conditions, there must exist a specific set of those perpendicular vectors, a frame that satisfies their F-dependency consistency condition.
Okay, so we're using these big theorems, Stiefel manifold, Borsuk-Ulam, to show that F-dependency consistency actually works.
You got it. It's a pretty intricate argument.
It definitely sounds like it. But, there's one specific thing in the definition of F-dependency consistency that caught my eye. It mentions a number, k plus 1, dk, dim, rf plus 1. What's the deal with that?
Ugh, good eye. That number, it's a bound. It limits the size of the groups of sets that we have to check when we're looking at this F-dependency consistency.
So like a way to simplify things.
Yeah.
Make the calculations easier.
Exactly. It tells us we don't have to check every single combination of sets, just groups up to a certain size. And that size depends on KD and whether we're working with real or complex numbers.
So it's like narrowing down the search, making it manageable.
Right. And this bound is super important in their proof. It plays a crucial role.
I see. All right, so we've laid the groundwork. We've got these definitions, these key theorems. I think we're ready to dive into the proof itself, aren't we?
Let's do it. It's where things get really interesting. All right, so the way McGinnis and Sadovek prove their theorem, it's pretty clever. They use a proof by contradiction.
Proof by contradiction, a classic. Assume the opposite and see where it leads you.
Exactly. So they start by saying, okay, let's assume our family of convex sets, they call it F. Let's assume it doesn't have a k-transversal. And then they show that this assumption leads to something impossible.
So if it leads to a contradiction, the original assumption must be wrong.
That's the idea. Now, to help visualize this, they take our family of sets, F, and they put it into a higher dimensional space.
A higher dimensional space. So like if our shapes are 2D, they bump them up to 3D?
Something like that, yeah. They embed them into this copy of F within a D plus 1 dimensional space, which they call ED plus ED plus 1.
ED plus ED plus 1. Okay, keeping track of all these terms.
I know, it's a lot. But basically, think of it as giving our shapes an extra dimension to play around in.
Gotcha, so more room to maneuver.
Right. Now, remember the Stiefel manifold we talked about before?
The catalog of perpendicular vector orientations?
That's the one. So for each dk orthonormal frame in that manifold, they define a subspace, which they call V, that's spanned by those vectors.
So a V, it's like a slice of this higher dimensional space. Okay.
Exactly. A slice determined by those specific vectors we pick.
Okay, I'm picturing it. What do they do with these slices?
Well, here's where it gets interesting. For each convex set F in our family, they find a special point.
A special point. How do they find that?
They project each shape onto our subspace V and find the point within that projection that's closest to the origin.
So like shine a light on the shape, see where its shadow falls on V, and pick the point in the shadow closest to the center.
Perfect analogy. They label this point PVF.
PVF. Gotta love those mathematical labels.
Right. But these points, they're crucial for their proof. They use them to build a map. They call it their test map.
A test map? What's that all about?
This map, it takes a dk orthonormal frame from the Stanel manifold and maps it to a point in another higher dimensional space, fk plus 1 dk. And the formula for this map, it involves those special points, the PVF and the map, from our definition of F-dependency consistency.
Okay, so we're taking information about the shapes, projecting them, finding special points, using those points to create this map. I'm following the steps, but what's the goal here?
The goal is to get a contradiction. Remember, we're assuming that our family F doesn't have a k-transversal.
Right, proof by contradiction.
Exactly. By building this map, they're able to use a theorem, theorem 3.3 in the paper, which is related to the Borsuk-Ulam theorem.
Okay, back to Borsuk-Ulam. It's all connected.
It is. And this theorem helps them show that this test map must send some dk frame to the origin.
So we've found a specific set of vectors, a frame, that makes our test map output the origin. Why is that a big deal?
Because then they show something really important, the vector ed plus 1. Remember that unit vector pointing in the d plus 1th dimension?
Right, ed plus 1, got it.
They show that ed plus 1 cannot be contained in the subspace V that's spanned by this specific frame that gets mapped to the origin.
Okay, so ed plus 1 can't be into V. Why not? What happens if it is?
If it was, then all those special points we found, the PVF, they would all lie in a d-dimensional subspace of ed plus 1. And if that happened, a certain sum involving those points wouldn't equal 0.
And that would be a problem.
A big problem. It would contradict the way they define their test map.
So ed plus 1 being outside V is essential to make everything work, like a crucial puzzle piece.
Exactly. Now, they then focus on the sets in our family F, whose projections onto V don't contain the origin. They call this subfamily G.
Why just those sets, though? Why not all of them?
Because if the origin was in the projection of every set, we could easily find a k-transversal.
Wait, really? Why is that?
Think about it. If the origin's in the projection, that means there's a point in the original set that, when projected, lands right at the origin. And that means there's a k-transversal. We'd be done.
Oh, I see. So they're focusing on the harder case where that easy solution doesn't exist.
You got it. Now, because the projections of these sets in G don't contain the origin, we know there must be certain inner products that aren't 0.
Inner product's the way we measure how much two vectors point in the same direction, right?
That's right. And because these projections don't contain the origin, the special points and the vectors in our frame can't be perpendicular, so their inner products can't be zero.
Makes sense. Where do we go from there?
This is where they use Carathéodory's theorem.
Another theorem. Hit me with it. What's Carathéodory's all about?
Basically, it says that if you have a point inside a shape made by connecting other points, you can always express that point as a combination of a limited number of those other points.
Like if a point's inside a triangle, you only need the 3 corner points to define it.
Exactly. You don't need all the points on the sides of the triangle, just the corners.
Okay, so how does that apply here?
Remember, our test map sent a specific frame to the origin. Well, Carathéodory's theorem lets them find a smaller group of sets, they call it F, that can express the origin as a special combination of points.
So we've narrowed it down even further, from F to G to F.
Right. And because F is F-dependency consistent, they know there must be other points, which they call QF, within the sets in F that satisfy certain relationships.
So we're linking points from our projections to actual points within the shapes.
That's the key. Now, if we project these QF points onto V, we get an equation. It looks like this. F, F, FEO are FEF, F true, UFPF, PVFEO, AV 0.
Whoa. Okay, lots of symbols there. Break it down for me.
No worries. It's basically saying that if you add up a bunch of terms, and each term involves those projected points, QF, and our special points, PVEF, that sum has to be 0.
Okay, adding things up and they should equal 0. What's the problem then?
The problem is that each term in that sum, it has to have a positive real part.
Hold on, why is that?
Because of how we chose those special points, PVF, remember they're the closest points to the origin within each projection. Because of that, the inner product between proj QF and PVF has to be positive.
Because of the geometry, it forces that inner product to be positive.
Exactly. So we're adding up a bunch of positive things, and they're supposed to equal 0. That's impossible.
It's a contradiction. Our initial assumption must have been wrong.
Exactly. So if F is F-dependency consistent, it must have a k-transversal.
Wow. We went through a lot there. So many steps, so many theorems.
It's a complex proof, but a really elegant one.
It is. But, I always got to ask, what's the impact of all this? What can we actually do with this knowledge?
It's a big result. It solves a problem that's been around for a while, Finding a condition like this for k-transversals has been a real challenge.
It's got to feel good for mathematicians to finally have an answer to that.
Definitely. Plus, it opens up a whole bunch of new research directions.
Like, what kind of stuff could people explore now?
Well, for one, figuring out how hard it actually is to find these k-transversals. The theorem tells us they exist, but actually computing them, that's another story.
So it's like, we know there's treasure out there, but no map to find it.
That's a good way to put it. And then there's the question of generalizations. What happens if we tweak the assumptions a bit? What if the sets aren't convex anymore?
Yeah. Or what if we're working in a completely different kind of space?
Exactly. And there's the potential for applications, too, outside of pure math, I mean.
Oh, yeah. Like where?
Well, transversal theory pops up in computer graphics, robotics, even medical imaging.
Wow. So this could have some real-world impact.
It could. New algorithms for things like collision detection, maybe path planning.
That's pretty cool. Taking abstract math and putting it to use.
It is, isn't it? The authors actually point out a few interesting research directions in the paper itself at the very end.
Let's hear it. What do they suggest?
One thing they bring up is, can we understand F-dependency consistency in a more intuitive way? Right now, it's a bit abstract.
Yeah, I can see that. Like, is there a way to think about it in terms of simpler arrangements of points or lines, something more visual?
That's what they're wondering. They also mention this other result, a colorful generalization of the Goodman-Pollack-Wenger theorem.
Colorful. What does that even mean in this context?
So colorful, it means you've got multiple families of sets, each with its own color, and you're looking for transversals that intersect sets from different families in specific ways.
So like red circles, blue squares, and you want a line that goes through at least one of each color.
That's the idea. As a whole new layer of complexity, right?
For sure. So they're asking, can we do something similar with their k-transversal theorem?
Exactly. A colorful generalization, it's an open question.
I bet some folks are already working on that as we speak.
Probably. They also talk about this other open problem, about finding one-transversals, just lines, that intersect families of disjoint unit balls in d-dimensional space.
Disjoint unit balls, those are just spheres that don't overlap, right?
Yep, all the same size, no touching allowed.
So the question is, can we always find a line that goes through every single one?
That's the challenge. We know some things about how many balls you need to guarantee a line exists, but the exact numbers are still a mystery, especially in higher dimensions.
So there's this gap in our knowledge.
Yeah.
And they think F-dependency consistency might help us fill it.
That's their hope. It might be the key to understanding these one-transversals in a new way.
Well, that's definitely something to think about.
Hmm.
It's so cool how this one paper could solve one problem and lead to the solution of others.
It really shows the power of math, how everything's connected.
It's been awesome exploring all this with you.
Yeah.
I feel like I've learned so much about k-transversals and this whole area of math.
It's been a pleasure diving into this paper with you.
And to all our listeners out there, thanks for joining us on this deep dive. We hope you learned something new and interesting today. Keep sending us your questions, your papers, your sources, and we'll keep exploring them together. Until next time, happy mathing. All right, strap yourselves in because today we are going deep into higher dimensional geometry.
Sounds fun.
We got a request to do a deep dive on a paper called A Necessary and Sufficient Condition for K-Transversals.
Yeah, that's a good one.
It looks pretty intense.
Yeah, it's a really interesting paper. It basically tries to figure out when we can find these higher dimensional objects called transversals that intersect a bunch of shapes.
Okay, so just to be clear, like when we talk about transversals, we're talking about things like lines, planes, but like also their higher dimensional equivalents. And those things have to cut through a given set of shapes.
Exactly.
Got it.
And what's really cool about this paper is that it looks at this problem not just in the regular real spaces that we're used to, but also in complex spaces, which adds a whole other layer of complexity.
Oh, wow. Yeah, it's amazing how much there still is to figure out about even like basic geometry concepts.
Totally.
So can you maybe set the stage for us a bit? Like, what's the existing knowledge in this area, and how does this new research fit into the bigger picture?
For sure. So the first thing we need to talk about are k-transversals.
Yeah, okay.
The k here refers to the dimension of the object that's intersecting our sets.
So like a line cutting through would be a one transversal.
Exactly.
Oh.
A plane intersecting some 3D objects would be a two transversal, and so on.
Got it.
Now, one of the most important results in this whole area is Helly's theorem.
Oh, yeah, Helly's theorem. That's like a classic. It seems so obvious, but then when you try and actually prove it,
it's trickier than you think.
Yeah.
Basically, Helly's theorem is all about the case when k equals 0.
Okay.
So our transversal is just a single point.
Right.
And it says that if you have a bunch of convex shapes and every subset of D plus one of them share a common point, then all of those shapes must intersect at a single point.
Oh, that's kind of cool. So like if you can guarantee that any small group of them have a point in common, then they all have to have one in common.
Yeah. It's like finding common ground, but in a geometric sense.
I like that, yeah.
So that's Helly's theorem. Then we have the Goodman-Pollack-Wenger theorem, which looks at D1 transversals.
Okay, so one dimension lower than the space you're working in.
Exactly. So for example, finding a plane that slices through a bunch of 3D objects. And this theorem uses something called order type, which is a way of describing the relative positions of those objects.
So it's like how they're arranged in space dictates whether or not you can find a plane that cuts through all of them.
Yeah, exactly. If the arrangement allows for a D1 transversal, this theorem says it must exist.
Okay, that's pretty cool. So we've got a theorem for 0 transversals and a theorem for D1 transversals. What about everything in between?
Well, that's where this new paper comes in.
Right.
It's all about finding a general condition for any k-transversal, where k can be anything between 0 and D1.
Oh, wow. So this is like filling in a big gap.
Exactly. And they do this in a really elegant way by introducing this new concept called dependency consistent with dk tuples in a finite set of points P.
Okay, that's a mouthful.
Yeah. It sounds kind of intimidating, but it's actually really powerful.
All right. So what on earth does dependency consistent even mean?
Okay, so imagine you have your collection of convex sets, let's call that F, and then you have the separate set of points, P.
Okay.
Now, to be dependency consistent, you basically need to assign each set in F a point from P.
Oh, so like each set gets its own little representative.
Exactly. And the key is how these representatives behave in terms of linear combinations. Let's say you take a bunch of sets from F and you express them as a linear combination that equals 0. If you then take the corresponding points in P and they also sum up to 0 in the same way, then we say those sets are dependency consistent with those points.
Okay, let me make sure I understand. So you're saying that if the sets themselves have this like summing to 0 property and their representatives in P mirror that, then something cool happens.
Exactly. It means that you can find a similar summing to 0 relationship among points chosen from inside those sets.
So like this abstract property of the representatives tells us something about the sets themselves.
Yeah, and what's remarkable is that this condition actually encodes information about whether or not those sets can be intersected by a k-dimensional transversal.
Wow, okay, so this seemingly simple condition about summing to 0 is actually telling us something really profound about the geometry of these sets and these higher dimensional objects. That's amazing.
Yeah, it is. And what's even more impressive is that this condition actually generalizes both Helly's theorem and the Goodman-Pollack-Wenger theorem.
Oh, wow. So it's not just like a new thing. It's like a unifying framework for all of these previous results.
Exactly.
Okay, so this dependency consistent condition is clearly like the key to unlocking this whole problem.
Totally.
But I imagine actually proving that it guarantees the existence of a k-transversal is where things get really hairy.
Oh, yeah. The proof is where things get really exciting. They bring in some pretty heavy-duty tools from topology, including something called the Stiefel manifold and the Borsuk-Ulam theorem.
Okay, that sounds pretty intense.
It is, but we'll go through it step by step. Basically, what they do is they use what's called a configuration space test map scheme. They basically build this mathematical machine that takes the information about our sets and translates it into the language of topology.
Oh, so they're like creating a dictionary between shapes and these abstract spaces.
Exactly. And then by using this map, they can leverage the power of the Borsuk-Ulam theorem to prove their result.
Okay, I am very intrigued.
Yeah.
But I think maybe we should leave it there for now. We'll pick back up and dive into that proof in part 2.
Sounds good. Welcome back. We're in the thick of it now, trying to figure out how to prove that this dependency consistent condition actually guarantees that we can find a k-transversal. And let me tell you, the proof is pretty wild.
Yeah, you mentioned Stiefel manifolds.
Yeah.
The Borsuk-Ulam theorem, it all sounds a bit intimidating, to be honest.
Oh, it definitely is. But we'll take it step by step. So as I said before, the whole proof hinges on this idea of a configuration space test map scheme. They're essentially building this mathematical machine that takes all the geometric information about our sets and translates it into the language of topology.
Okay, so it's like a bridge between the world of shapes and the world of like these abstract topological spaces.
Exactly. And the first thing they do, which is a very common move in math, is they start with a proof by contradiction. They assume that there isn't a k-transversal for our sets.
Right. So start by assuming you're wrong and then see where that leads you.
Yeah, it's like a detective story. You're following the clues until you find the inconsistency. Now, to make things a bit easier, they actually embed our sets into a slightly higher dimensional space.
Okay.
So instead of working in ARD or CD, they put everything into a copy of that space, but sitting inside a d+1 dimensional space.
So it's like taking a 2D drawing and putting it on a 3D table. You're giving yourself an extra dimension to play with.
Exactly. And this is where they introduced this concept of a DK orthonormal frame. Remember those Stiefel manifolds we talked about?
Yeah, they were like each point on the manifold represents a way to arrange a bunch of perpendicular vectors.
Right. Each point represents one of these frames. So you can think of it as a bunch of arrows all pointing out from the origin, and they're all perpendicular to each other.
Okay.
Now, each frame defines a subspace, let's call it V, that's spanned by those vectors. So it's like a lower dimensional slice of that d+1 dimensional space.
Oh, okay. So it's like taking our higher dimensional space and slicing it with a plane, and that plane is determined by those vectors in the frame.
Precisely. And for each of our convex sets, they project it onto the subspace V and find the point in the projection that's closest to the origin. They call this point PVF.
I see. So like if you shine a light on our higher dimensional shape, its shadow falls on V, and the point in that shadow closest to the origin is PVF.
Exactly. Now, here's where it gets really clever. They use these closest points and the points from P, the representatives of our sets, to define a special map.
So this is the test map, the one that links the geometry to the topology.
Exactly. So this map takes a point on the Stiefel manifold, which represents a specific orthonormal frame, and it sends it to a point in another space that encodes information about both the closest points and those representative points from P.
Okay, so each arrangement of those vectors gets translated into some other mathematical object that captures what's going on with the sets.
Right. And this is where the Borsuk-Ulam theorem comes in.
Yeah, you said it was like crumpling up a sheet of paper.
Yeah, basically the Borsuk-Ulam theorem says no matter how you crumple up that sheet of paper, two opposite points on the original sheet are always going to end up touching in the crumpled version.
Right, so there's always going to be some overlap no matter how you try and distort it. But how does that apply to this map?
Well, in our case, the Borsuk-Ulam theorem guarantees that there must be a specific point on the Stiefel manifold that gets mapped to the origin by our test map.
Okay, so there's some spiral arrangement of vectors that gets sent to 0. Why is that important?
Well, this particular point, with its corresponding subspace V, creates a situation where those closest points, the PVFs, can be combined in a way that sums up to 0. And even more importantly, the corresponding points in P, the representatives, also sum up to 0 in the same way.
Hold on, isn't that what the dependency consistent condition is all about? Didn't we say that if the sets and their representatives in P both have that summing to 0 property, then something special happens?
You got it.
What was it again?
It means you can find a combination of points from inside the sets that also sums to 0. It's like the summing to 0 property gets passed down from the representatives to the sets themselves.
Okay, I see where you're going with this, but didn't we also say that the origin can't be contained in any of the projections of our sets onto V? Otherwise, we'd already have a transversal?
Exactly, and that's where the contradiction comes in. See, if the origin is outside a convex set, and you pick the closest point in that set to the origin, any other point in that set has to lie on the same side of a hyperplane through that closest point.
So it's like all the other points are above that hyperplane if you think of the closest point as the lowest.
Exactly. And because of that, any combination of those points with positive coefficients can never sum up to 0.
I get it. So the dependency consistent condition says we should be able to find a combination that sums to 0, but the geometry says we can't.
It's a contradiction, and that means our initial assumption that there's no k-transversal must be wrong.
Wow, so we've proven that if a family of sets is dependency consistent, there has to be a k-transversal.
We've proven the only if part. We still need to prove the if part, which says that if a k-transversal exists, we can always find a set of points in a mapping that satisfy the dependency consistent condition.
Okay, so it's like the existence of a transversal guarantees those special points. Is that proof as complicated?
Fortunately, no. If we have a k-transversal, we can just choose points inside each set that lie on that transversal. Then we can map those points to any k-dimensional space using an affine isomorphism, which preserves all the properties we care about.
So we're projecting those points from the transversal down onto a lower dimensional space, and that automatically satisfies the condition.
Exactly. So we've proven both directions. This dependency consistent condition is all you need to determine if a k-transversal exists.
It's amazing how they took this idea of point summing to 0 and used it to say something so deep about geometry.
It is pretty remarkable. But this is just the beginning. The paper also talks about some really cool implications and open questions that come from this result.
Well, let's hear them, but maybe we can save that for part 3. Welcome back to the show. I feel like we've really been on a mathematical adventure here.
Oh yeah, we've gone deep.
We've explored the history of the k-transversal problem, we've wrestled with this new dependency-consistent condition, and we've seen how it can be used to prove some pretty amazing things. But where do we go from here? What are the broader implications of all of this?
That's a great question. And, the paper actually highlights a few really interesting directions for further research. One of the things they talk about is the difficulty of finding a purely combinatorial interpretation of the dependency consistent condition.
Yeah, we talk about that a little bit. It's like, how do you translate this condition from the language of linear algebra, like all those vectors and sums, into something that's more about counting and arrangements?
Exactly. And they're not very optimistic about the chances of finding a really simple interpretation. They point to a previous result that says there's no Hadwiger-type theorem for one-transversals in three-dimensional space. These Hadwiger-type theorems are all about finding transversals based purely on how points are arranged.
Oh.
So the fact that such a theorem doesn't exist for this case suggests that the problem of finding k-transversals might be inherently more complex than just looking at arrangement.
So it's like the dependency consistent condition is capturing something deeper about the sets themselves, not just how they're positioned relative to each other.
Exactly. It's a real challenge, and I think it's going to keep mathematicians busy for a long time to come.
I bet. You know, it's funny. It's like every time you solve a problem in math, it opens up a whole bunch of new ones.
Yeah, it's kind of the beauty of it, isn't it?
Totally. Now, didn't they mention something about a colorful generalization of the theorem? What's that all about?
Yeah, so colorful is this kind of fun term that's used a lot in combinatorial geometry. Basically, imagine that you have several families of sets, and each family gets assigned a different color.
Okay.
A colorful transversal would then be one that intersects at least one set from each color class.
So it's like a rainbow transversal, has to hit all the colors.
Yeah.
That sounds a lot harder.
Yeah, it definitely adds a new layer of complexity. But what's interesting is that there's already a colorful version of the Goodman-Pollack-Wenger theorem. So naturally, you might wonder if you can do the same thing for this new theorem as well.
That would be really cool. I'm guessing the proof would be even more intense, though.
It would be quite a feat, that's for sure.
Yeah.
But who knows what kind of applications a colorful generalization might have.
That's true. It's often the most abstract stuff that ends up having these surprising connections to other areas.
Absolutely.
Now, you also mentioned an open problem about uniballs. What was that about?
Right. So there's this result about families of pairwise disjoint unit balls in d-dimensional space. It says that if you can arrange the balls in a line, and every group of second balls has a one transversal that respects that order, then the whole family has to have a one transversal.
So it's like if every sufficiently large chunk of that line of balls can be pierced by a line in the right order, then the whole thing can be pierced.
Exactly. The problem is that we know the constant Tugend cannot be lowered to 2d2, but we don't know if it can be lowered to 2d1.
Oh, okay.
And what's interesting is that when you look at their theorem for the case of k equals 1 in real space, the constant they get is precisely 2d1.
Oh, wow. So their result might actually be the key to solving this problem.
Yeah, it's a pretty tantalizing connection. It really shows how interconnected math is. Like what seems like a pure theory problem can have these really concrete applications.
Well, I've got to say, this whole deep dive has been pretty incredible. We've explored the history, we've grappled with some really complex concepts, and we've even caught a glimpse of some of the open questions that are still out there. It really makes you appreciate the power of math to unlock these deep truths about the world.
It really does.
And who knows, maybe one of our listeners will be inspired to pick up the torch and solve some of these mysteries themselves.
That would be amazing.
Until next time, keep those brains buzzing and keep exploring the fascinating world of math. Welcome back to another deep dive. Today we'll be looking closely at this paper you sent over, a necessary and sufficient condition for k-transversals.
Yeah.
You know, and the reason you sent this to us is you're working on a problem that needs you to understand when a family of convex sets actually has a k-transversal.
Mm-hmm.
So we're going to unpack that today.
Yeah.
And I'm thrilled to have our math expert with us today to help us, navigate this dense world of k-transversals.
Yeah, always ready for a math challenge.
Absolutely.
Okay.
So before we jump into the paper itself, let's, I guess, recap for our listeners what k-transversals are all about.
Yeah.
And I think we can think about them like lines, planes, or even higher dimensional spaces that intersect every object in a given collection. Is that right?
Exactly. And, the k in k-transversal refers to the dimension of that intersecting space.
Got it.
So, like, a one transversal would be a line that goes through all of them, a two transversal, a plane that slices through them, and so on.
Okay. And so the tricky part is figuring out when such a transversal exists. I mean, we know there are solutions for specific cases like Helly's theorem,
Right.
Which deals with finding that common point.
Yeah.
And the Goodman-Pollack-Wenger theorem,
which
deals with D1 transversals in a d-dimensional space, but this paper is aiming for something a bit more comprehensive. Right?
Yeah. It's giving us like a general tool to find out, if there's a k-transversal for any value of k, so between 0 and d1.
Okay.
And they do this in both real and complex spaces.
Interesting.
Yeah.
Okay, so let's dive in. Page 1. The abstract, they lay out their main achievement, a necessary and sufficient condition for a k-transversal.
Right.
So basically they have a condition and it's like if it holds, you guarantee a k-transversal.
Yeah.
If not, you're sure there isn't one.
Exactly. It's like if you have all these objects, and then you have like this magic sword that slices through them all, you have to like figure out if the sword actually works,
Right.
Like if it can actually slice through them.
Yeah. So it's like a test for the magic sword.
Exactly.
Okay, got it. And they say the result, generalizes both Helly's theorem and the Goodman-Pollack-Wenger theorem, which I think is fascinating.
Yeah. Really shows the power of this result because those are like two different theorems, but they're kind of connected under this one umbrella.
Right.
It's really cool.
Okay. Well, one thing I will say, just looking ahead, they mention using a Borsuk-Ulam type theorem on Stiefel manifolds as a key tool. Now, already I'm a bit intimidated, I'll be honest.
Don't worry. We'll get to that later.
Yeah.
It sounds scary, but it's a powerful tool, like a lever to, prove big things.
Okay. All right. I'm ready to be levered. So page 2, they talk about the history of k-transversal research. Yeah. And they start by mentioning Vincenti's question.
Yeah.
About a constant that, could guarantee the existence of a k-transversal.
Yeah. Vincenti thought there might be like some easy way to just look at the number of sets that have a transversal and be like, oh, there's got to be one for the whole thing. Right. But Sandel showed that wasn't true. You can't just rely on numbers like that.
Right. So it's not that simple.
No, it's more nuanced.
Okay. And then they bring up Hadwiger's theorem, which, focused on one transversals for disjoint convex sets just in the plane. Yeah.
So Hadwiger kind of figured out that order was important. Like, if you can order the sets a certain way and any three have a line going through them in that order, then they all must have a line. Huh. It's like lining up dominoes, If they're set up right, one push knocks them all down.
Okay.
It's all about getting that order right.
Got it. So it's that consistent ordering idea. That's theorem 1.1. So you need to find that ordering that works for all the sets, right?
Exactly. You got to make sure all the dominoes are in line.
I like it. Okay. And then we get the Goodman-Pollack-Wenger theorem, which extends Hadwiger's work to higher dimensions and overlapping sets.
Yeah. More powerful, but it's still about that order, just in a more abstract way.
Okay. So then we get to page 3, and they start talking about order type, which basically generalizes linear ordering.
Yeah, like, things on a line have a natural order, but what if they're in 3D space?
Right.
Order type lets us capture that relative position without getting bogged down by, like, coordinates.
Got it. So it's like a map, but just for positions, not distances.
Exactly.
Then there's definition 2.1, which is separates consistently.
Yeah, this is making sure that the way we arrange our points, it actually reflects the way the sets themselves are arranged.
Okay, so like if we're trying to represent buildings on a map, we want them to be laid out in the same way.
Exactly. Like a good city map should tell you how the buildings actually are.
Got it. Okay. And then they use that in theorem 2.2, which is the Goodman-Pollack-Wenger theorem. And it basically says if you've got a set of points with an order type that matches the sets, then you've got yourself a D1 transversal.
Right. It's like if the map is accurate, you can find a path that goes past every building.
Perfect. Okay. But then they bring up proposition 2.3, which is like a linear algebra way of looking at it using affine dependence.
Right. So instead of thinking about points visually, it's like, can we write them as combinations of each other?
Okay, so we're switching from pictures to equations.
Yeah, it's more powerful. And it helps when we move to complex spaces.
Ah, okay. Interesting.
Yeah, that's what they do next.
All right, so let's head to page 4. They jump into complex spaces now, right? They're defining convex sets in C8T that's d-dimensional complex space.
Yeah.
So it's like Alice through the looking glass, right? Everything's familiar, but there's this extra complexity because of the complex numbers.
Exactly. It's like we added another dimension, but with some extra rules to follow.
Okay, got it. Then we've got dependency consistent in definition 2.4 for complex spaces.
Yeah.
It seems like they're basically taking that linear algebra idea and adapting it for complex dependencies.
Right. Generalizing it so it works for both real and complex vector spaces.
Okay.
Crucial step towards their main result.
All right. And they wrap up this section with theorem 2.5, which is essentially the complex version of the Goodman-Pollack-Wenger theorem, right?
Exactly. So now we have tools for finding D1 transversals in both real and complex spaces.
Okay. So a lot of groundwork here. We've got the history, the key concepts, the theorems.
Yeah. The foundation is set. Now we're ready for the big reveal, their condition for any k-transversal.
That sounds exciting.
It is. It's the key to unlocking the secrets of these transversals.
All right. Well, we're going to take a quick break, and when we come back, we'll dive into the core of this paper.
Okay, so let's jump into page 5. And this is where things get really interesting. So they introduce this concept in definition 3.1. It's called F dependency consistent with DK tuples.
Okay.
And this is really the heart of their discovery.
Okay.
It might seem a bit intimidating at first glance, but it's worth breaking it down carefully.
All right, I'm ready to break it down.
So you remember how we talked about affine dependence? Like, do those points all lie on a line or a plane or some lower dimensional space?
Right. That idea.
Well, this definition is kind of taking that idea and applying it to groups of points instead of just single points.
So instead of asking if 3 points lie on a line, we might ask if, 3 groups of points, each with 5 points, are arranged in a specific way.
Exactly. Right.
Right.
And the F dependency consistent just tells us if we're working with real numbers or complex numbers, like what's the underlying field.
Got it. I'm looking at the notation here, and it's definitely dense. Can you give us, like, a high-level view of what it's trying to say?
Sure. Basically, it's saying that if you have a family of convex sets, and you can map those sets to groups of points, like DK tuples, in a way that preserves certain affine dependencies, then we call that family F dependency consistent.
Okay, so what kinds of dependencies are we talking about here?
So we're looking for dependencies within each group of points. Like, are those points dependent on each other? And also dependencies between corresponding points in different groups. So it's like, how do those points relate to each other within their group? And then how do they relate to points in other groups? And the definition lays out very specific conditions on these dependencies.
Can we try and visualize this at all? Like, is there an analogy we could use to kind of wrap our heads around this?
Okay, let's try it. Imagine each convex set is like a planet. And then each DK tuple of points is like a constellation of stars orbiting that planet. So definition 3.1 is kind of laying out rules for how those constellations can be arranged relative to each other, both within their own planetary system and across different systems. And if the constellations follow these rules, then the family of planets or convex sets is F dependency consistent.
Ah, I see. So it's like these abstract rules about how these groups of points are allowed to relate to each other.
Exactly.
Okay, that's helpful. So this definition, it seems very abstract, but it's actually describing very specific relationships between these points.
Yes, and the amazing thing is that this abstract condition turns out to be tied to the existence of k-transversals. It's like a bridge between how those sets are arranged and whether there's a space of a certain dimension that cuts through them all.
Okay. And that's where remark 3.2 comes in.
Yes.
It's showing us how this definition actually brings together Helly's theorem and the Goodman-Pollack-Wenger theorem as special cases.
Exactly. It's like we found a more general rule that includes those older theorems.
All right, I like it. Okay, let's move on to page 6. Now we encounter this Stiefel manifold. Which the name itself sounds a little intimidating.
It does sound a bit mysterious, doesn't it? But it's actually not that complicated. Basically, the Stiefel manifold represents all the ways you can choose a set of orthonormal vectors in a given dimension.
Okay, so if we're in 3D space and we have 2 vectors, the Stiefel manifold represents all the ways we could arrange those 2 vectors.
So
they're perpendicular to each other and they both have length 1.
Exactly. It's like a catalog of all the possible frames you can make using a fixed number of vectors.
Okay. Interesting. Now, theorem 3.3 brings up this Borsuk-Ulam type theorem for Stiefel manifolds.
And
it seems like this is a key part of their proof.
It is. This particular Borsuk-Ulam theorem basically says that if you have a continuous map in the Stiefel manifold to a certain kind of space, and it respects certain symmetries, then that map has to hit the origin of that space.
Okay, so it's like a rule about these mappings that have to meet certain conditions.
Exactly.
Okay. But how does this theorem help us with the k-transversal problem?
Well, that's what the proof of theorem 3.4 is all about. They're going to build a map that fits the Borsuk-Ulam theorem and then use it to show that assuming there's no k-transversal leads to something impossible.
So it's like a proof by contradiction.
Exactly. Assume the opposite and show it breaks down. And the Borsuk-Ulam theorem is the tool to make that happen.
Got it. So on page 6, they start the proof, assuming F, our family of convex sets, doesn't have a k-transversal. And they make some simplifying assumptions. They say the sets in F are compact so they're closed and bounded.
Yes.
And they embed them in a higher dimensional space.
Gives them more space to work with.
Okay.
Like more room to maneuver.
Got it. So we've set the stage. What's the next move?
So for every possible dk orthonormal frame, which is like a set of perpendicular vectors, they define a subspace V, spanned by those vectors, and then they project each set onto this V, like shining a light and looking at the shadows.
Ah, I see. So they're taking these high-dimensional objects and looking at their lower-dimensional shadows.
Exactly. Reducing the dimensions.
Okay, and then for each set F, they define this point PVF.
Yes.
Which is the point in the projection that's closest to the origin.
Right, like finding the point in the shadow that's closest to a fixed light source.
Got it. Now remember that map from definition 3.1?
Yes.
The one that maps each set to a dk tuple of points.
Right, the one with those specific dependencies.
Yeah, exactly. Well, they use that map along with those special points PVF to build a new map called a test map.
Yes.
Which goes from the Stiefel manifold to some Euclidean space.
Right. So they're taking those frames from the Stiefel manifold and using them to create points in another space, using information from the sets and those special points.
Okay, so they're combining information from different places to build this new map.
Yeah, and here's the crucial part. This test map is what's called z-equivariant.
Okay, remind me what equivariant means again.
It means the map respects certain symmetries. Like if you flip the sign of a vector in the frame, the output of the map changes in a predictable way.
Okay, so it has this built-in symmetry based on how the input changes.
Right, and this symmetry is key for using the Borsuk-Ulam theorem.
Ah, okay, so they've set up this map that fits the theorem's conditions.
Exactly, they've laid the trap.
Got it.
Now, on page 7, they spring it. They apply Borsuk-Ulam to this test map and show there must be a special frame that maps to the origin.
So this is like the smoking gun.
Yes.
Yeah.
And it leads to a chain of consequences that break down our initial assumption.
Okay, I'm on the edge of my seat. Tell me more.
First, they prove that the vector ed plus 1, which is that extra dimension we added, can't be in the subspace V.
Right.
If it were in V, it'd mean all our projected sets were actually in the original space.
Right. Which would mean a k-transversal exists.
Exactly. So that can't be true.
Okay.
Next, they show that there's at least one set whose projection doesn't contain the origin, meaning that special point PVF, the one closest to the origin, is not actually at the origin.
Right, because if they were all at the origin, it would mean they all intersect there.
Exactly. And again, a k-transversal would exist.
Okay, so they're ruling out these possibilities.
Yes, tightening the net.
Got it. So what happens on page 8?
Okay, on page 8, they define a subfamily G, which are all the sets whose projections don't contain the origin.
Okay.
And then they use Carathéodory's theorem to express the origin as a combination of points from this G.
Remind me what Carathéodory's theorem says.
It basically says if a point is in the convex hull of a set, then you can express it as a combination of a smaller subset of those points.
Okay, so it's like simplifying.
Yeah, focusing on the important parts.
Got it.
And this leads them to a set of affine dependencies, both in the original space and in the space of those dk tuples.
Ah, so they're using that F dependency consistency definition now.
Exactly. And this is where the trap closes.
Okay.
On page 9, they manipulate those dependencies using projections and inner products, and they end up with an equation that just can't be true.
They've created a mathematical impossibility.
Exactly. This contradiction proves our initial assumption wrong.
So there must be a k-transversal.
Yes. We've come full circle.
That was quite the journey.
It's beautiful how they weave together all these ideas.
Okay, let's take a moment to digest all of that, and then we'll come back and explore the implications of this theorem. Welcome back. I feel like we just climbed a mathematical mountain walking through that proof, but it was worth it. I mean, we really got to see the depth of this problem.
Yeah, it was a challenging proof for sure, but so elegant.
Okay, so let's turn to page 10, where they finalize the contradiction. It's all about projections and inner products.
Right. They show that assuming no k-transversal exists leads to a statement that contradicts how inner products work, especially with complex numbers.
Okay.
And that forces us to give up on our initial assumption.
So the only option left is that a k-transversal must exist.
Exactly, like a chain of logic leading to the inevitable conclusion.
I like it. And they even give us figure 1 to help visualize that last step.
Right. Yeah, figure 1 shows the relationship between the projections and inner products, making that impossible inequality clearer.
Right, because sometimes it helps to have a visual.
Definitely, especially with abstract concepts.
Okay. So let's move on to page 11, where they wrap things up with some concluding remarks.
Okay.
One thing they point out is that while definition 3.1, the core of their result, it's a powerful condition, but it doesn't have that simple combinatorial feel, like the separates consistently idea from Goodman-Pollack-Wenger.
Right. It's definitely more abstract, but also more general.
Right. It works for both real and complex.
Exactly. Sometimes pushing the boundaries of math means encountering ideas that are inherently more complex.
I see. They also mentioned that there's no Hadwiger-type theorem for one-transversals in 3D.
Yeah.
Meaning a condition just based on points might not be enough for that case.
Right. It shows there are still open questions in this field. Plenty of room for more research.
And they propose a really interesting open problem, too. Can their theorem be generalized to a colorful setting?
Ah, yes, where the sets have colors and the transversal has to intersect specific color combinations.
Exactly. It adds a whole other level of complexity.
Definitely. Imagine the implications for problems with multiple types of objects.
Right, where you need a transversal that hits certain combinations. It's fascinating.
Absolutely. So many possibilities.
Okay, and lastly, they suggest applying their theorem to finding one-transversals for disjoint unit balls.
Yeah, a concrete example of how their abstract theorem can be used.
Okay, and on page 12, we have the authors themselves, Daniel McGinnis and Nikola Sadovek.
Both leading figures in discrete geometry.
Absolutely. So, stepping back, we've explored this paper that presents a truly powerful theorem. It definitively solves this question of k-transversals.
And it's not just a solution. It's a potential key to new discoveries in other fields.
Like computer graphics.
Yeah, data analysis, all sorts of areas.
It's been a deep dive into this amazing world of geometric transversals.
It really shows how math can unlock the secrets of the universe.
Thanks for joining us on this mathematical adventure.
It was a pleasure.
Until next time. Welcome to another deep dive. Today we're going to be looking at k-transversals.
Okay.
You gave me this paper, A Necessary and Sufficient Condition for K-Transversals.
Right.
By Daniel McGinnis and Nikola Sadovek.
Yeah.
Sounds a little complicated, but I'm sure we can break it down.
Yeah, this paper's kind of cool. It generalizes like Helly's theorem and the Goodman-Pollack-Wenger theorem for like any dimension.
So maybe before we even jump into the paper,
sure,
can we define what a k-transversal is?
Oh, yeah. So
like it's a refresher.
The simplest way to think about it is you have some family of shapes, and then a k-transversal is like a k-dimensional flat object that intersects every member of the family.
Okay.
So, for example, if you have like a bunch of circles in the plane and you have a line that passes through all of them,
right,
then that line would be like a one-transversal.
Okay, so a line's a one-transversal. What would be like a two-transversal?
The two-transversal, you could think about like a plane. So if you have a bunch of spheres in 3 space and you have a plane that intersects all of them, that plane would be like a two-transversal.
I see. So it's just a matter of like what dimension object we're talking about.
Exactly.
That's intersecting the other objects.
Yeah, and the K just tells you what dimension the object is.
Okay.
That's intersecting the other shapes.
Gotcha. And this paper basically gives us a way to know if a family of shapes even has a k-transversal for any k.
That's exactly right. Yeah.
Okay, cool. So jumping into the paper.
Okay.
They start off in the introduction. They mention Helly's theorem and the Goodman-Pollack-Wenger theorem.
Right.
And they say that these are specific cases of k-transversals.
Yeah.
Could you just elaborate on what that means?
So Helly's theorem, like the simplest version of it, is you have a bunch of convex sets in like d-dimensional space.
Okay.
And if every d plus one of them intersect, then they all intersect.
Right.
That's Helly's theorem. And so that's the case when k is equal to 0.
Okay.
Because your transversal is just a point. It's a zero-dimensional object.
Right.
Okay.
And then the Goodman-Pollack-Wenger theorem, it deals with the case where k is equal to d1.
Gotcha.
So you have some family of like convex sets in d-dimensional space, and every d of them have a hyperplane transversal. Then they all have a hyperplane transversal.
Okay. So those two kind of cover the extreme cases.
Exactly.
K0 and KD1.
Yeah. And so
what about everything in between?
This paper is basically about all the values of k in between.
Okay. That's what this paper addresses.
Yeah, exactly.
Cool. So now they get into like the meat of the paper. They're introducing this new condition.
Right.
It's definition 3.1.
Yes.
F dependency consistency with DK tuples.
Yeah.
I'm already a little lost just reading that. So can you break that down for me? What does that even mean?
So basically you have like some family of convex sets in art.
Okay.
And we're trying to decide if there exists a k-transversal to this family.
And the way we're going to do that is by assigning like each set F to a point in RK using this function.
So we're assigning a point to each of these shapes.
Exactly. And we're assigning a point in k-dimensional space.
Okay.
And then this condition about F dependency consistency is basically saying that if you have certain relationships between these points in RK, then the corresponding sets back in ARC have to have a certain relationship.
Okay, give me an example of that.
Okay, so like, for example, suppose that you had DK plus 1 sets from your family, and their corresponding points in RK, like if they all lie on a hyperplane of dimension DK.
Okay.
Then the condition is saying that the intersection of those DK plus 1 sets has to be non-empty.
So it's like,
does that make sense?
Whatever is happening with the points in RK is telling us something about what's happening with the shapes in ARC.
Exactly. That's exactly right. Yeah. And it's not just about hyperplanes. It's about like more general dependencies involving DK tuples of points in RK and how their corresponding sets depend on each other.
Gotcha. Okay.
So does that make sense?
Yeah, I'm starting to see how that would be a condition for this transversal to exist.
Yeah, because it's like if you can find some kind of function where like all these dependencies match up in the right way, then that's basically telling you that there should exist a k-transversal.
Gotcha.
Yeah.
And they show that in remark 3.2.
Right.
This actually encompasses both Helly's theorem and the Goodman-Pollack-Wenger theorem.
So in remark 3.2, they basically show that their condition implies both of those theorems.
Okay.
And it kind of gives you like a sanity check.
Gotcha.
The condition makes sense because, you know, like if it didn't imply those theorems, then you'd be like, well, something's wrong here.
Right.
But it does.
Right. Okay. So they introduce this condition and it kind of makes sense intuitively.
Right.
But now they got to prove that it actually works.
Exactly. Yeah. And so like the proof is really interesting.
Okay.
It uses this thing called the Stiefel manifold and like a Borsuk-Ulam type theorem.
Okay, well, let's stop there for a second. What is the Stiefel manifold?
Yeah, so the Stiefel manifold...
Maybe some of our listeners haven't heard of that.
So imagine you have like d-dimensional space.
Right.
And you want to choose k orthonormal vectors.
Okay.
The Stiefel manifold is basically like the set of all possible ways you can do that.
Gotcha, okay.
So each point in the Stiefel manifold is like a set of k orthonormal vectors.
Okay, I see. So like if you think about it as like a coordinate system or something, it's all the different ways.
Exactly. It's like all the different
to find that coordinate system.
Frames of reference you can have.
Okay.
Yeah.
All right, and what about this Borsuk-Ulam theorem?
Yeah. So the Borsuk-Ulam theorem, basically it says that if you have a continuous function from a sphere to a Euclidean space of a smaller dimension, then there have to be two antipodal points on the sphere that get mapped to the same point. Okay. So antipodal just means like...
Right, on opposite sides of the sphere.
Yeah, on opposite sides of the sphere.
Okay, gotcha. And how do these very abstract seeming concepts relate to k-transversals?
So basically what they do is they construct this function called the test map. Okay. And it goes from the Stiefel manifold to like a smaller dimensional Euclidean space. Okay. And the idea is that like each point in the Stiefel manifold you can think of as being like a DK dimensional subspace of RD plus 1. Okay. And then they use this test map to kind of like see if that subspace can be like extended to a k-transversal.
I see.
Does that make sense?
Mm-hmm. Okay. So it's analyzing if that DK subspace be a k-transversal or not.
That's exactly right. Mm-hmm. And then like the Borsuk-Ulam theorem comes in because it tells you that there have to be two antipodal points in the Stiefel manifold that get mapped to the same point under this test map. Okay. And then they show that if there is NO k-transversal, then that creates a contradiction.
So it's like they set a trap.
Exactly. It's like
Borsuk-Ulam theorem.
Proof by contradiction.
Okay. Yeah. Can you actually walk me through how that contradiction rises?
Yeah.
Because they mention figure 1.
Yeah, it's just a figure
as being like a key part of that.
It's like a geometric picture of what's going on. Okay. But let me try to explain it.
Okay. Let's dive into the visual details there.
So the idea is that you have these two antipodal points in the Stichel manifold. And you project onto the dk dimensional subspace corresponding to one of the points.
And you do it in a way so that one of your sets like projects onto a point. And another set projects onto a set containing the origin. And then because those 2 points in the Stichel manifold get mapped to the same point under the test map, if you project onto the subspace corresponding to the other point, you have to get the same thing. Like one set projects onto a point and another set projects onto a set containing the origin.
So you have these two different projections, but
But they both have the same property.
Behave the same way.
Yeah, exactly.
Gotcha.
And then that's where the contradiction comes in. Because if you look at it carefully, that forces those two sets to intersect.
Can you walk me through the specifics of how that happens?
So like, let's say your first projection is 1 and your second projection is 2. And let's say that like F1 is the set that projects onto a point.
So then there has to be some point X in F1 so that 1X and 2X are both equal to that point.
So you have this one point in F1 that gets mapped to the same location. In both projections.
That's right, And then let's say that F2 is the set that projects onto a set containing the origin. So then there's some point Y1. So that 1Y1 is 0. And there's some point Y2. So that 2Y2 is 0. Does that make sense?
So you have two different points that get mapped to the origin. And this is where the contradiction comes in.
So like, basically, because 1X and 2X are equal, like the line segment connecting them has to pass through 0. But that line segment also has to lie entirely in the projection of F2. Because it connects...
Because the 2 points are both in F2.
Exactly. But then, like, because projections preserve convexity, that means that, like, if you take the preimage of that line segment under either projection, it also has to lie entirely inside of F2. But the preimage of 1X is just X, which is in F1. And the preimage of 2X is also X, which is in F1. So then that line segment has to contain a point in F1, but it also has to lie entirely inside of F2.
So you've shown that F1 and F2 intersect.
Yeah, exactly.
When we assume they didn't.
Yeah, exactly. And that's a contradiction.
That's really cool.
So yeah, so that's basically the idea of the proof. It's like a really clever geometric argument.
So I love that they use these kind of like...
very sophisticated tools.
From topology.
And the Stichel manifold to kind of like force this contradiction.
It's like they're really bringing in a lot of different machinery to solve this problem. So we've covered the introduction, the new condition they introduce, and the really interesting proof they construct.
So now we've like gone through the proof, which was kind of a journey in itself.
Very elegant.
So just to kind of recap, like what they've done is they've given us this condition that tells us when a family of convex sets has a k-transversal. And this is like really nice because it works for any value of k. Like it generalizes all those previous theorems that only worked for like specific values of k.
It's really cool how they pull in all these like tools from like geometry, topology, linear algebra.
It's a very nice blend
to come up with this
in different areas of math.
And then one thing I really like is that they also highlight in the concluding remarks, like new questions and research directions.
There's a lot of really cool open problems that they mention.
So it's like solving this one problem kind of like opens up this whole new...
area of use.
There's kind of answered one question, but they've opened up like 10 more.
Exactly. It looks like climbing one mountain and realizing...
And then you see a whole mountain range.
There's this whole mountain range that you hadn't even seen before. So let's dive into some of those concluding remarks. One of the things they mention is the lack of a combinatorial formulation for their new condition.
So, like, the Goodman-Pollack-Wenger theorem, it has this very nice, like, geometric interpretation. You can think about it in terms of, like, arrangements of points and things like that. But their condition, it's more algebraic. It's about... like these matching functions and how they depend on each other. So it's not clear if there's like a nice combinatorial way to think about it.
So it's like...
we have this tool.
Yeah.
It works.
It's powerful, but we don't really...
But we're still kind of figuring out...
understand it fully.
Use it.
Yeah, exactly. And the authors say that, like, finding a combinatorial interpretation might actually be really hard.
Gotcha. Okay.
Like, it might be impossible for some values of K.
Okay. Interesting.
Yeah, so that's a cool open problem. Like, is there some hidden geometric structure that we just haven't found yet?
Right. So they've given us this map, but...
They've given us the map, but some of it's blank.
Some of it's blank.
Yeah.
Exactly. And then they also hinted this colorful generalization of their theorem.
So that's another really cool thing. Like, in recent years, there's been this trend of looking at colorful versions of these, like classic combinatorial geometry problems.
Okay.
And so the basic idea is, like, you assign colors to your objects, and then you want to find, like, a transversal that intersects objects of different colors.
Gotcha. So it's not just, like, making the math look pretty.
Yeah. No. It's
actually adding this whole other...
a whole other layer of complexity.
Layer of constraints.
Yeah. And a lot of times it leads to really surprising results.
Okay.
And so the authors suggest that, like, their theorem might have a colorful generalization.
I see. Okay.
So, for example, suppose you had a family of, like, red and blue convex sets.
Okay.
Instead of just asking, is there a k-transversal?
Right.
You could ask, is there a k-transversal that intersects at least one red set and at least one blue set?
Oh, that's a cool, like, twist on the original problem.
Exactly. Yeah, so there's all these different...
Like, what other color variations can we come up with?
And maybe they lead to, like, even more interesting adventure.
Okay. The last open problem they specifically mention is about finding the minimum number of unit balls required to guarantee the existence of a one transversal.
Yeah.
Can you remind me what unit balls are?
So a unit ball is just like a ball of radius 1 in d-dimensional space.
Okay.
So, like...
And why is this problem so interesting?
So this is a really classic problem in combinatorial geometry.
Okay.
And, like, basically you're trying to find the smallest number of unit balls.
Okay.
So that if that many have a one transversal, then they all have a one transversal.
Okay. So it's like...
Does that make sense?
Finding that minimum number.
Yeah, exactly. It's like a Helly type theorem for unit balls.
Okay.
And it turns out, like, computing this number is really hard.
Okay.
Especially in high dimensions.
I see.
Yeah. And so
the authors suggest that their results might help with this.
They think that, like, maybe their new theorem could give some insight into this problem.
It's really cool how they take this very general result.
Like, it's amazing how
it connects to this very specific problem.
This very specific problem.
Yeah.
That's one of the things I really enjoy about math is these connections between the general and the specific.
Me too. Yeah. It's like...
And how...
That's what makes math so powerful.
It all ties together.
Yeah, exactly.
This has been a really great deep dive. I feel like I understand k-transversals much better now.
Yeah, this is a really cool paper.
But I want to talk a little bit about, like, the computational implications.
Yeah, that's a good point.
Of these results.
Like, the paper is very theoretical.
Yeah.
But it's natural to ask, like, can we actually use this to compute k-transversals?
Right. Like, if you give me a big data set of objects and you say, does there exist a k-transversal for some k?
Yeah. Can you actually find it?
Can I actually find it?
Can we write an algorithm to do that?
Yeah. So that's a really good question. And it's not clear immediately from the paper how to do that.
Right. So maybe we need to, like...
Yeah, like, one thing you could try to do is, like, reformulate their condition in a way that's more computationally tractable.
Okay. So turn it into, like...
Yeah, like, maybe turn it into, like, a system of equations or something that you could actually solve.
Or inequalities or whatever.
Yeah.
Okay.
That's one idea. Another idea is, like, maybe you could try to use their proof to actually construct the k-transversal.
Yeah, because they used, like...
Yeah, like, maybe all this topology and stuff.
Yeah.
So maybe that...
Maybe there's some algorithm hidden in there that we haven't found yet.
Okay. Very cool. Well, this has been a really fascinating paper.
Yeah, it's really...
I enjoyed a beautiful blend of...
talking about it with you.
Different ideas from different areas of math.
It's a great paper. So thanks to everyone for listening. We hope you enjoyed...
Yeah, thanks for listening.
...this deep dive into k-transversals.
Yeah.
And we'll see you next time.
See you next time.